Hello, this is Mrs. Taylor, and I am going to help you answer the question, how do derivatives help us determine a function's concavity? Just a quick reminder what concavity looks like graphically. If a function is concave up, I usually think of it as like the u is up, so it would be like this. Concave down, the u is upside down. And then you could have a combination. You could have concave down and then concave up all in one curve. So this would be up, down, and then this would go from down to up. A concavity defined in words. Let f be differentiable in an open interval I. That means it has smooth turns. There's no corners, cusps, or discontinuities. And the graph is concave upward on the interval if the derivative is increasing on the interval, and concave downward on the interval if the derivative is decreasing on the interval. So recognize it's saying the derivative is increasing or the derivative is decreasing. So when we're thinking about the derivative increasing or decreasing, we're thinking about the derivative slope. And remember, to find the slope of the derivative, you use the second derivative. So when f prime is increasing, the second derivative would be positive, and when f prime is decreasing, our second derivative would be negative. And so that takes us to the test for concavity. And so the test for concavity is defined as, let f be a function whose second derivative exists on an open interval I if f double prime x is greater than 0. So if the second derivative is positive for all the x values in the interval, then the graph of f is concave upward in the interval. And if the second derivative, f double prime of x, is less than 0, so if it's negative for all the x's in the interval, then the graph is concave downward. So basically, this is similar to testing for intervals of increase and decrease of a function. It's just now our conclusion will be whether a function is concave upward or downward. And so we're going to create a sign chart again, but this time for the second derivative, not the first derivative. So if our problem is determine the open intervals on which the graph of f of x equals 12x minus x cubed is concave upward or downward, we want to find the second derivative and create a sign chart. So first let's find the second derivative. My first derivative using the power rule would be 12 minus 3x squared, and then my second derivative would be negative 6x. So now I want to create a sign chart for the second derivative, and in order to do that, first I have to find my critical values, and remember that is where the derivative or the second derivative is undefined or equals 0. So negative 6x will never be undefined, but it will equal 0 at x equals 0. So that is our critical value. And so for my sign chart, that will be the one value I place on my sign chart. And remember, you want to label these, what they represent. This is f double prime, or the second derivative, and I have 0. And then I need to evaluate the second derivative to at a value to the left and to the right of 0. So the second derivative at negative 1 would be, and really remember, only thing we care about is it positive or negative? That would be positive. And then the second derivative at 1 would be negative. So it would change from a positive to a negative. So what this means is to the left of 0, my second derivative is positive. And according to this, if it's positive on an interval, concavity is defined by intervals, not by specific x values. But on that interval, my function would be concave upward. So f is concave upward from negative infinity to 0, and concave downward from 0 to infinity. So I'd write out my conclusion as the function is concave upward on the interval negative infinity to 0, and concave downward on the interval 0 to infinity. One other item that's really important that they didn't really ask for here, but that you are going to have to be aware of is points of inflection. And if you think back to Algebra 2 or pre-cal, you should remember that a point of inflection is where the concavity changes. So if it changes from concave upward to concave downward at x equals 0, then x equals 0 is a point of inflection. And remember that a point has an x and y coordinate, so point of inflection, plug in the x value 0 into the original function, get the corresponding y value, and you can define your point of inflection as the point 0, 0. And so that is how you would determine a function's concavity using the derivative.